Good afternoon, everyone, and welcome to today's webinar on maximizing efficiency, harnessing the power of VLAM Supercomputer Center for CFD Analysis, presented by Daikin. I'm very glad to be your host, and I'm excited to explore how we can leverage the capabilities of the VLAM Supercomputer Center to enhance our computational fluid dynamics analysis. Well, nowadays we are diving into a world where efficiency is paramount, where every computational cycle counts, and where the pursuit of optimization drives innovation. At Daikin, we understand the importance of pushing the boundaries of what's possible in CFD analysis, and that's why we have partnered with VSEC, a leading edge computing facility, to harness its immense power for our simulations. Throughout this webinar, we will go over the workflow. Let me see if I can take a laser. Okay. We will go over the workflow we follow while using the VLAM Supercomputer Center and uncovering its potential to drive efficiency in CFD simulations. Moreover, I will explain the existing technology at Daikin for CFD simulation, specifically here in Belgium in our EuroCC DEME department, diving deep into a case of study and finishing with some recommended best practices. Well, just to give a little bit of a background, how we ended up using the VLAM Supercomputing Center, I would have to explain that in the last 5 years, as part of the design process within Daikin, there has been a higher demand of CFD simulations. Computational fluid dynamics has become a strategic step in the design process. It enables us to analyze in detail the behavior of certain processes or the impact of design changes on important physical phenomena. Moreover, it has proven cost reduction and efficiency improvement, as we can substitute some tests and prototype making by using this kind of digital tools. Another important point has been that other departments inside Daikin have also started to implement CFD, such as, for example, Cenote in Italy, AHT in Austria, the ACC in Czech Republic, and the MGG in Germany. And finally, the problems we solve have become every time more computationally expensive. We are tackling quite complex engineering issues, or the models themselves have become very heavy mesh or very complex 3D geometries itself. Because of this, then the computational resources we were locally using started to become rather unhelpful. So we saw an opportunity to join with VSEC and use its power for our simulations. Since June 2022, Daikin has been using the VSEC Tier 1 cluster, and during this time, more than 20 different CFD projects have been developed. More than 5 million CPU credits have been used, such as 1,000 credit hours. This type of network interface that we currently use, it allows us to count with a safe and constant connection to our license servers and the storage center and to Star-CCM itself, which of course has resulted quite helpful for us. Now, maybe let's take a deeper look at the steps we typically follow to conduct our CFD simulations. First, we access the HPC Tier 1 website to check the available resources, and depending on the complexity of the case we're analyzing, we then submit an interactive session request. This request specifies the cluster we plan to use, along with details like time, number of nodes, and cores. The session request operates on a queue system, meaning that our session begins based on resource availability. We can also reserve resources in advance to avoid long waiting times. And once our session starts, we can launch then the cluster desktop. Inside the cluster desktop then, we will have access to the Linux interface, and with some basic codes, we can launch the user interface of a Star-CCM. It's even possible to create a default script which automatically runs the corresponding license and select the desired amount of resources to use. This makes the process to follow quite automatic and easy. And once the Star-CCM is launched, we have direct access to the program. I personally find this very beneficial because as engineers, we might need to verify results or the progress of the simulation in real time. We can even make changes in the simulation case directly in the cluster, while in other cases, we would have to do all this in advance or wait until the end of the simulation to check the corresponding results. Finally, we can export the results directly to our local network to proceed with post-processing and data analysis. In this case, we show the program recommended by VSCC, WinSCP, which allows a smooth and fast file transfer. So, in a nutshell, we have experienced several benefits from the use of the VSCC cluster. No deep coding knowledge is required. We can receive fast and support from the VSCC office team. We can effortlessly manage the session resource allocation, interact directly with the user interface from SimCenter Star-CCM, and monitor in real-time results we have. As you all are probably already aware, CFD simulations are highly computationally expensive and require parallel computation most of the time to reduce the time to complete and reach to a converged solution. SimCenter Star-CCM can be run in parallel mode, so providing a scalable solution to solving problems faster and to attempting larger and complex models. Then the use of VSCC becomes essential to run efficiently these type of simulations. So then what do we gain from all this? So efficiency of these simulations can significantly reduce computational time, which directly translate to cost savings. Shorter simulation times mean quicker results, faster decision making, and design improvement. Moreover, if the optimal number of resources is used, this will also allow to have some cost savings. And in the industry, there is a constant need to improve designs and make the products faster. With more efficient simulations, engineers can run multiple design iterations within a shorter time frame. And this allows for quicker exploration of design alternative, leading to improved product designs and faster time to market. Also, an effective scalability in CFD allows for larger and more complex models without sacrificing performance. Scalability ensures that the simulation remain accurate and reliable even as the size and complexity of the simulated system increase. Efficiency of the simulation make better use of available computational resources, including hardware infrastructure such as CPUs and GPUs. Companies as Daikin or organizations can achieve higher and better return on investment from the computational resources, in this case, the Blam Supercomputer Center. Efficiency in CFD simulations enables engineers to focus more on analyzing results and making informed decisions rather than waiting for simulations to complete. This leads to faster problem solving and decision making process. In general, organizations that can conduct CFD simulations efficiently gain a competitive edge in their respective industries. They can innovate more rapidly, optimize product designs faster, and deliver superior products or solutions to market ahead of competitors, which of course we as Daikin, that's what we want to achieve. Then, complex geometries and complex mathematical models require the use of high computational tools, such as those from the Blam Supercomputer Center. I'm going into more detail about what is done in Daikin regarding CFD analysis. We wanted to present in a summarized way the main type of investigations we focus on. So we have aeroacoustics, for example, that we use for the analysis of our outer units, fan rotation, thermofluids, where we analyze any type of problem where we need certain kind of flow characterization or heat transfer issue. We also use multi-component models, which we include for refrigerant leakage analysis or any type of mixture analysis. Also, multi-phase problem, as the picture we show here, when we analyze particle treatment, for example, specifically for weather resistant tests that we have to do to our units. And finally, design optimization, where we perform or parametric analysis or we use the adjoint model or topology optimization approaches. Now, to showcase in more detail what I have been mentioning so far, we wanted to go over a case of study. In this case, a refrigerant leakage analysis. The leakage and direct emission of refrigerants and refrigeration, air conditioning, and heat pump systems increase the greenhouse effect and pose a big threat to the ecological environment and the human health. Moreover, refrigerants present different degrees of flammability, increasing their impact on safety and risk assessment. For this reason, it's necessary to comply with the different standards, created safe designs, and giving the right instructions to clients and installers. For this purpose, we can perform leakage simulation, which allows to evaluate different conditions for refrigerant leakage without creating any real harm to the environment or human health. It doesn't involve physical resources, such as, for example, the use of units or refrigerant charge, and it gives an overall view of refrigerant behavior that couldn't be possible to get from a test where just the refrigerant concentration can be measured with sensors. Leakage simulation, however, can be quite challenging due to different factors, such as, sorry, I cannot, suddenly I lost my screen. Okay, I got it again. Such as heavy mesh models, because in the leakage simulations, we need to include small gaps. For example, we have to include the environment continua. We also use complex mathematical models as multi-component, for example, because we are analyzing the effect of the air and the refrigerant itself. We also use ideal gas models because we want to analyze how these gases are influenced by the temperature and pressure change, also heat transfer convection, turbulence models, gravity, and of course, these cases are all of them on steady analysis. And also the validation and of these simulations is very difficult. It's quite hard to be able to represent accurately the conditions of the test. So in general, it becomes very challenging. This results in a very long analysis, which can take sometimes weeks of calculation if not done using the appropriate resources. For this reason, then, we did kind of a study of how long it takes us and how expensive it is for us to do one of the simulations, depending on the resources that we use from the VLAM Supercomputer Center. For example, our reference case on our local remote desktop, it would be this dot we have here. It used to take around, I think, more than 2 weeks to do one of these simulations, while when using several nodes from the VLAM Supercomputer Center, we passed to less than 24 hours. We did a study of how expensive this was for us, and we kind of reached an agreement of the amount of nodes that would be possible for us to use, considering the time that we wanted to have during one of the simulations. Now, going into more detail to explain the case of study. This, for example, is one of our units. This is a cassette unit that is used for commercial applications. And normally we would start with kind of more simple basic simulation where we analyze the impact of the flow. We see temperature changes. We see if our original model is working, predicting correctly the test results we have. This is basically a cooling effect, for example, what you can see. And once we are sure about the results we get there, which are more easy to compare to test results and to real measurement, then we pass to the more complex part where we would have to include the multi-component model. For example, here we can see already the results of a leakage simulation. Normally, what we do here is that we need to include the multi-component model, we include the ideal gas model, and we simulate the real conditions of the specific refrigerant that we would want to study during a leakage case. We put the correct temperatures, the correct pressure. Also, for example, if you see here, this would be like a normal room. You can see there are 2 vents here, and this means that the ventilation system of the room would be also working. During the simulation, we monitor several probes that are included in the room, which then it's possible to compare to some test results. From those probes, we can measure the concentration of the refrigerant during time, how it changed during the simulation, but we can also see what is the overall behavior of the plumb of leakage. This is something that, of course, from a test, it's not visible. So it becomes quite useful for us to see what is the behavior of during a normal leakage. Where does the plumb is going? When do we start to have a higher concentration? What is the concentration of the leakage in the openings of the room? So it's very useful information that normally, of course, from a test we couldn't have. Also, in this case, we see the temperature variation during the leakage process because the leakage is coming at a different temperature than the one that the room is at the beginning. We can also create different thresholds to tackle like volumes at different concentrations of the refrigerant and see, okay, at what moment do we have the room more between this and this concentration? What is the actual volume or the actual mass of the specific refrigerant that we're having on those zones? So it's quite useful, all the information we can get from these. Also, we can see during time how this changes, and we can kind of recreate in an accurate way the test itself. Having access to the VLAM Supercomputer Center, it was possible to use then an efficient iterative approach. So normally we can simulate different room designs. Let's say we can very easily change the boundary conditions, where in this case we have a ventilation opening. Maybe for another case we actually put just a closed window, or we can put an pressure outlet in some different point. So we can very easily change all these parameters without having to create a real prototype of this, or without having to make changes in a test room and wasting certain refrigerant or certain gas. Also, we can vary the operation conditions. We can check what happens if at the beginning the room is at certain temperature, what happens if we have a certain pressure there, what is the impact from this problem itself. And also, of course, the leakage conditions. It's not the same if you have one refrigerant or another, if you have the refrigerant coming from a certain temperature or a certain mass flow, also if the leak area change itself. So it's possible to create different cases, which in this case, for example, for this study, we ended up analyzing more than 10 cases, and each one of them was taking like around 24 hours to simulate for 10 minutes simulations. So very helpful for us. Now, based on the different investigations we have done using the cluster from the VLAM Supercomputer Center, we can then recommend some best practices to make a more efficient use of the resources, licenses, and the credits itself. First, well, it's very important to prepare the simulation case in advance. This includes geometry modification, mesh settings, continua, boundary conditions. Prepare all the corresponding reports, field functions, plots, scenes that then will be needed from the simulation case. Once you have these, then of course, pass it to the VLAM Supercomputer Center, import it there like a clean case, so it's also faster just to copy the case there. And you're ready then to mesh and run. Optimize the mesh density, try to fine tune the mesh density based on the specific requirements of the simulation. Use mesh refinement techniques judiciously to capture important flow features while minimizing the computational overhead. Utilize symmetry, of course, take advantage of symmetry in the geometry or flow field whenever possible to reduce the computational resources and simulation time. Start from simple to more complex, kind of similar to what I was showing before. Begin by modeling the flow without including complex features such as energy equation and so, and gradually incorporate additional complexities like energy equations and say solvers, depending on what's needed, and ensure that each step aligns with the simulation objectives. Then Monitor convergence. Continuously monitor the simulation convergence criteria and adjust the solver settings as needed to achieve convergence efficiently without sacrificing accuracy. In this case is where I think it becomes very important the fact that with the VLAM Supercomputer Center you can have access directly to the user interface of a Star-CCM, and you don't really have to wait till the end of your simulation to be able to check these parameters. Of course, manage the data output, control the frequency and format of the data output during the simulation to avoid excessive storage requirements and minimize post-processing time. Selectively save only essential data for analysis while discarding unnecessary information. And of course, export the result data for post-processing, take it back to your computer, and analyze in detail in a local server to avoid using more credits from the VLAM supercomputer. Document the simulation workflow, maintain detailed documentation of the simulation workflow, including setup parameters and solver settings. These facilitates reproducibility, collaboration, and knowledge transfer. Maybe it sounds like an obvious thing, but when you're trying different things or you start to have problems with the simulation and you keep changing things, sometimes it becomes hard to remember what we were doing and what we changed at the end.